Greetings, math scholars. This is lesson 5-6, the inverse of a function. In this lesson, we're going to be taking a look at how we find what is called an inverse function. And I got to be honest with you, folks, it's really easy to find the inverse of a function. All you do is switch x and y. That's it. Switch x and y. Now, what we want to talk about, though, and get into the more specifics, is an inverse function switches the role of x and y. What that means is the input becomes the output, and the output becomes the input. It's like we flip-flop the two. I have some notation here. So f of x is equal to the regular function, and this right here next to it is the notation for the inverse function. So it's f, and then it looks like it has an exponent of -1, but that's just the symbol for inverse. So f inverse of x is how I would say this right here, f inverse of x. So it looks like I said, f to the negative first and then parentheses x. It's like function notation, but just a little different. I'm going to show you how to find an inverse 3 different ways using a function, a graph, and an equation. So first we'll take a look at the table of values. So like I said, all you do is you flip your x and your y. So for this first point right here, -6, 4, I flip x and y. That becomes the point -4, -6. For the next point, -5, -2, I switch the x and the y. It becomes -2, -5. Boy, folks, this is really tough. I'll just go through and fill in the rest of my table for you right here by flipping the x and the y values for each and every single one of these points. I get each one of them to switch the x and the y's. Whew. Wow. Okay, that was tough. Next one. We're now going to find the inverse using a graph. So you'll see here that I have the line. Oh, by the way, those are the same coordinate values from the table values before. You're welcome. And what we're going to do is we're going to flip the x and the y values. So what this is graphically, though, is really just a reflection over the line y equals x. That's what this blue line is right here. This blue line right here is the line y equals x. So when we flip the x and the y values, we actually are reflecting over the line y equals x. That's kind of important here. But when I go through here, so I'll come up with the point -6, -4. That turns into the point -4, -6. That's right here. That's -4, -6. Next point, next point. That is -5, -2. So that goes to -2, -5. That's there. Okay, next point. 0, -4 is where that point would be after I do a little switcheroony, right? And from here, hopefully, we can start to see what happens when I flip each one of these individual points. So 4, -2. Now I'm at 6, -1. Oops, 6, -1. My bad, that was not 6. Let me erase that here quick. Boop. Okay, go away. My mistake. Next guy here, 8, 0. Okay, that's this point right here. And now when I connect the dots, let's see what I end up with. Whee! Looks like that. Okay. Okay, so my line's not perfect, but I wanted to show you what it looked like if it was perfect. There you go, and I have labeled all of the coordinate pairs there for you and everything. So again, what you'll notice is I flip the x and the y, and it's a reflection over the line y equals x. That's kind of cool what ends up happening. Each one of those points gets reflected over, and it goes to a different spot. Neat. Okay, one more thing. Find the inverse using a function. Okay, f of x equals 2x plus 8. Spoiler alert, folks, that's the same equation that I used to generate the table of values and the same as the equation of that line that I had on the previous screen. Go back, check it out. I'm telling you, that's pretty cool. So what do? Well, when I have and need to find the inverse of a function using an equation, it's pretty easy. First thing I'm going to do is I'm going to change this f of x, I'm going to change it into y. So I write y equals 2x plus 8. Remember how easy I told you finding an inverse function is. You just flip x and y. That means the x becomes y and the y becomes x. So my equation, instead of it being y equals 2x plus 8, it becomes x equals 2y plus 8. Not bad, right? But that's a weird form that we have this equation in. So what we want to do is now we want to solve for y. We want to try to isolate y, get y on a side by itself. So we need to think about algebraically, how do I do that? So if I want to solve y, let's see, what am I doing to y? I'm saying I'm multiplying it by 2, and then I'm adding 8. So I want to undo the addition and subtraction first. So I'll subtract 8 from both sides. That gives me 2y on the right-hand side, and then I have x minus 8 on the left. I can't combine like terms. There's nothing like to combine there, so I'm not going to try to put them together. Okay, to get y by itself, one more step. I got to divide by 2. I got to undo that multiplication. So that gives me, finally, with my equation, y equals x minus 8 all over 2. That's a fine answer, folks. That would be acceptable for an inverse function. But I could also distribute the division and do x divided by 2 minus 8 divided by 2. Oh, what's that mean? Okay, so that gives me the equation 1/2 x minus 4. That's a better answer, but like I said, I would go back here and I'd accept y equals x minus 8 all over 2. And again, if you go back and look on the previous slide, what you would see is you would see that the line, that green line that I had there, is actually the equation for y equals 1/2 x minus 4. Go ahead, check it out. Go rewind the video. It's fine. I'll wait. All right, next, we're going to find the inverse function and then graph its inverse. So I would like you to pause the video right now. I'd like you to test out what we just learned. I'd like you to do these two equations and then make sure you graph them. Take time to graph them. Okay, pause the video now, and then I'll go over the answers. All right, first, number one, f of x equals 1/3 x minus 2. Okay, so we're going to go ahead and rewrite this as y equals 1/3 x minus 2. We're going to flip my x and my y, make my y equal to x and my x equal to y. And that gives me x equals 1/3 y minus 2. And I'll start solving this guy for y. So let's see here, that gives me 1/3 y equals x plus 2. And then how do I undo multiplying by 1/3? I know, I'll multiply by 3. That'll be so much easier. So that gives me y equals what? So distribute the 3, so I get 3x plus 6. Okay, so there's my equation. And I'd like to use the appropriate notation, so I'll rewrite that as f inverse of x equals 3x plus 6. I think it's a good idea to use the proper notation here. All right, so first of all, let's go ahead and graph this original function. I'm going to use my red color to graph f of x equals 1/3 x minus 2. That's here, that's a y-intercept of -2, and then I rise over run, so rise over run, and then I rise over run again, and I rise over run again. Okay, let me go ahead and get rid of my little test marks there so I can get rid of that so it's a little not as confusing when we see it. All right, and we'll go ahead and graph that. Let's see here, so okay, there's a line that goes this way. I think I need some more points so I can graph it a little more accurately. Okay, there we go. So there is f of x, and I'll go ahead and label that right there for you. And now I'll do f inverse of x, and that's 3x plus 6. So if I go ahead and graph that, let's see, that's a y-intercept of 6. And then I go up 3 and over 1. I better go the other direction, get some more points, so I can graph this a little bit more accurately. Let's see. Okay, so we go that way, and then we go down this way, and there we go, right there. And we'll label that as f inverse of x. Now, I didn't want to leave you hanging here, folks. I wanted to show you what this looked like, and there's what it actually looks like when I do it. Again, my green curve here is the inverse of f of x, and my blue line here is, of course, f of x. Okay, so you don't get confused at what you're looking at. And I also included this line right here. I included y equals x so that you could see the reflection over that line. On to example 2. All right, for example 2, g of x is equal to 2 times the square root of x minus 3. Folks, don't be afraid when you see the radical. Okay, we're not going to do anything different here, okay? I'll rewrite it, and then I'll switch my x and my y, so I'll make it x equals 2 square root of y minus 3. And I'll undo this equation just like I did in the last problem. So let's see here. I have to get rid of this 2, so I'll divide both sides by 2. Okay, dividing by 2 is the same as multiplying by 1/2. So I have 1/2 x equals the square root of y minus 3. Okay, I can't get to that 3 until I get rid of the radical. So what do? I square both sides. Now, remember here on the left-hand side, you have to square each thing individually. Okay, I have to square the 1/2, which gives me 1/4. And then I square the x squared, that gives me x squared. And then on the right-hand side, the squared and the square root cancel out. So I'm left with just y minus 3. Okay, one more step. I'll add 3 to both sides. That'll give me y equals 1/4 x squared plus 3. And I'll use the proper notation here. So f inverse of x is equal to 1/4 x squared plus 3. All right, so let's graph these. So for g of x, I'm going to use my red marker. And let's see here. Ooh, this is the square root function that has been shifted to the right 3 units. Okay. Now, that's a little tricky. So I think it might be a good idea if I also maybe think of a table of values for this function. So if I think of a table of values for this function, I know, for example, when I plug in 3, I get 0. What's another nice number? Ooh, 4. Maybe I'll try 4. Let's see here. So 4 minus 3 is 1. The square root of 1 is 1 times 2 is 2. So I get to the point 4, 2. That's going to be this point right here. Okay, what's the next thing? Well, 5 minus 3 is not a nice number. Neither is 6. But 7 minus 3 gives me 4. And the square root of 4 is 2. So then I get 2 times 2, which is 4. So my next point is 7, 4. Now, if you don't believe me with these points, go ahead. You create a table of values. It'll be okay. It'll work itself out. That's probably enough. I could do another point if I wanted to, but I think that's probably good. We get a good idea of what that looks like here. All right, there you go. There's that. Now, let's graph 1/4 x squared plus 3. Well, we got to be careful here. We got to be careful because if you notice and you remember that this is a reflection of this equation over the line, I have to be careful because I'm only going to end up graphing 1/2 of this equation. And my table of values is really helping me to be able to graph this. So I'm plotting the point 0, 3, 2, 4, and then 4, 7. Those are the opposite points that I had for my table of values right here. So there you go. That's a good idea of what that graph looks like. And again, I wanted to show you what it really looked like in Desmos here for you so that you weren't confused. So G inverse of x is the green one, and G of x is the blue one. Let's go back and look at the last two functions side by side here. So we have number 1 over here on the graph on the left, and we have number 2 here is the graph that's on the right. And what I want you to observe here is I want you to observe the fact that these are both functions and their inverse is also a function. So on this graph here on the right, if you look at the equation here for 1/3 x minus 2, that's this one, f of x, you'll see that it does in fact pass the vertical line test, right? Any vertical line, it's only going to pass through that thing once and only one time, okay? If I look at the other equation, if I look at the inverse of f of x, that's this green one right here, the inverse of f of x, you'll see again, it only passes through a vertical line one time. So that one passes the vertical line test. Now, I want you to observe this though, okay? I don't actually have to know whether a function, if its inverse is going to be a function. I can look at the regular equation to figure that out because we have something called the horizontal line test. So the vertical line test tells me if what I am currently looking at is a function, right? If a vertical line passes through a graph once and only once, then what we're looking at is a function. But the horizontal line test tells me whether what I'm looking at, if the inverse of what I'm looking at is also a function. So the inverse of a function is also a function if and only if no horizontal line intersects the graph more than once. So if I look at this, this is x to the third. The first graph is x to the third. You'll see that if I look at any horizontal line, this will pass through the graph once and only once. Therefore, the inverse of this graph is a function. And let me show you what the inverse graph of this looks like. So the third power, I'll give you a spoiler alert. The third power, the inverse of this is the third root of x. And we know what that graph looks like. That looks a little bit like this. I know it's not extremely neat, but you'll see that that doesn't pass the vertical line test. If we go over here to g of x, x squared, you'll see that, oh no, look, there's two spots where a horizontal line passes through x squared. Therefore, the inverse of y equals x squared is not going to be a function. Okay, and let me show you what that actually is. So if we switch x and y, if you trust me on this, what I would end up with for my equation is x equals y squared. And as we know, when I solve for y, I need to take the square root of both sides and remember the plus or minus. So my actual inverse of the graph of x squared looks like a sideways parabola. Okay, and if we look at that, that does not, in fact, pass the vertical line test, and therefore it's not a function. But we don't actually need to go through the headache of finding the inverse to know whether the inverse of what we're looking at is going to be a function. Just use the horizontal line test. The final thing with inverse is verifying inverse functions. And in order to verify that two functions are inverses, we have to do the composition of functions like we did in the last section. So you have to do f of g of x, and you have to look at g of f of x. If both of these functions, when you simplify them down, end up with x, then the two functions are inverses. So I want to show you that right now. So in this, we're going to verify that f of x equals 3x minus 1 and g of x equals x plus 1 over 3 are in fact inverse functions. Okay, first thing, let's do f of g of x. All right, so let's see here. That means I'm doing f of g of x is x plus 1 over 3. Okay, then we'll plug in, okay, so now we do plug in x plus 1 over 3 into my function f every time I see x. Okay, so that's 3 times x plus 1 over 3 minus 1. All right, so we'll do a little distributive property. Let's see here, this 3 and this 3 cancel out. So I'm left with x plus 1 minus 1 and x plus 1 minus 1. That equals x. Okay, cool deal. So f of g of x does in fact equal x. So far, so good. Well, now let's do g of f of x and see if we end up with the same thing. Okay, so let's see here. That would mean that I'm going to take and do, let's see here, f of x is equal to 3x minus 1. And in this particular equation, every time I see an x in g, I'm going to replace it with 3x minus 1. So let's see here. That means I got 3x minus 1 plus 1 over 3. Okay, well, these parentheses really aren't doing anything for me, so that's here. That would give me 3x minus 1 plus 1 over 3. The minus 1 plus 1, they cancel out. So I'm going to go up here. Let's see. So that gives me 3x over 3. The 3's cancel out, and I'm left with just x. So guess what? G of f of x is also equal to x. Since I got x both places, f and g are inverse functions. Hope this all makes sense to you. If not, go back, rewatch the video, ask me any questions you have. Folks, thanks for paying attention. See you later.